Hello guys, in this video we'll be formally introduced to linear combination, span and linear independence. Okay, so let's start with linear combination. So let us consider that our vector space V is R2. The vector looks like this as a tuple x comma y, and the field is the real numbers. Okay, now let me consider a vector. Okay, so let P be a vector from this vector space 1 comma 1. Then there is Q that looks like this. Now I can add these two. So this is the story from the beginning, right? We can add two vectors and we get this. Even better, we can multiply this with a scalar. So now 2 and 3 is a scalar that comes from the field, right? So here 2 and 3 comes from the field. There's this vector P and Q, and the result whatever we get also belongs to the vector space V, right? So this is the whole theory of vector space. Now linear combination is this. So 5 comma 8, the new vector, can be called as a linear combination of P and Q. Okay, why? So it's like this. So linear, this is linear, I mean 2, you're just multiplying with the scalar, so that's linear, and there's an addition as well, and there's a combination, so you're combining this vector and this vector, right? So there's a linear combination, and that's it. So 5 comma 8 is a linear combination of P and Q. Right. So, in general, say V is any vector space, can be polynomials, can be matrices, can be anything. Okay, any vector space, and actually the field also can be anything, not necessarily R, but it can be complex numbers as well. So whatever is the space, so field. So generally speaking, if P is a vector that belongs to the vector space V, Q is another vector that belongs to V, AP plus BQ is equal to R. Okay, so now A and B are coming from fields. Okay, these are scalars. They come from the field. P and Q are the vectors, and the linear combination of this is R. Okay, so R is the linear combination of P and Q. Okay, now this you can do it for n number of vectors. So that you have P1, P2 up till Pn. So these are n vectors in the vector space V, and you have n scalars, so a1, a2, an, all of these are scalars coming from the field, and you combine all of them, you get some s. Okay, so s is also a linear combination of all the pi's. Okay, so these are the different pi's. Okay, and you can also write them like this, right? So that was the general form of a linear combination. Now consider this. Say I have S. Okay, so again, my vector space is R2. A vector looks like this, and these are in the field. So now consider I have a set of two vectors. Okay, so this is my first vector, this is my other vector, and I call it S. Okay, so set of two vectors. Now I can multiply this with a scalar a1 and this with a scalar a2, and then I'll get some x. Okay, now what if I consider all possible values of a1 and a2? Okay, so a1 and a2 belongs to real numbers in this case. So I can go from minus infinity to plus infinity for a1 and minus infinity to plus infinity for a2, and I'll get different values of x. Okay, so now suppose for every value of a1 and a2, whichever value of x I get, I put them into a set. What do you think? How will that set look like? Okay, so that set is actually having a name, and that is known as the span of S. I'll tell you why it is span. So span basically means, in Hindi we can say pahach. So what is the span of the vector? How long can the vectors go? We can think it like that. Okay, so just let me quickly go to Desmos and I'll show you something. Okay, so these are the two vectors that I've plotted over here. So 0 comma 1 is the first vector, and 1 comma 0 is the other vector. Okay, now if you see, I have this black thing that is a1, a2. These are my multiplication factors. Okay, so what I've done is, the equation is over here. So I have two equations. One is a1 into this first vector. So if you see a1 into first vector, plus a2 into the second vector. Okay, so x2 and x1 are my two vectors over here. Okay, so if you see this, I can now have any possible values of a1 and a2 which I can control over here. Okay, and the output whatever I get c1 c2 is this black dot 1 comma 1. Okay, so for now a1 and a2 both are 1 and these are 0 comma 1 and 1 comma 0. So what I get is 1 comma 1 which is over here. Now I can move this from minus infinity to plus infinity, and you see I can span or I can reach the whole vertical axis, right? So A1 can make me reach the whole vertical axis. Now A2 can make me reach the whole horizontal axis, and accordingly I can actually span the whole space. So I mean, you choose the value of a1 and a2 and you can reach anywhere on this grid, right? So this is what we call as span. Okay, so these vectors, this and this, these two vectors can span the whole R2 over here because their linear combination can reach everywhere. Okay, so that is the physical significance of the span. Okay, you're spanning the whole space. Okay, coming back. Right, so that is span. So the span of S is now a set. So it is a set containing all possible values of a linear combination of X, I mean linear combination X containing all possible values of A1 and A2. So it will span the whole space. Okay. Again, talking generally, so where V is the vector space, any vector space, F is field. I mean, this also can be anything. And there are these AIs that are going to come, which are going to be in the field. So S is your set, which is having some vectors v1 to vn. These may be anything. Okay, don't just get into the notion of the tuple. You can have polynomials over here, you can have matrices over here, you can have functions over here. This is actually abstract. Okay, and the span of S is equal to all possible values of AI. Okay, so you have this linear combination and all possible values of AI. So actually this is a typo. Yes, there should be I. Okay, right, so I is equal to 1 to n. So for all possible values of AI, you will have this. Fine, so that is span. Okay, now span of S is a subspace of V. Okay, so V is my original vector space. So I'm taking some vectors from the vector space. Okay, and I am taking the linear combination of that. So span of S is a subspace of V. It should lie in V. You cannot go outside V. I mean, that's clear, right? Because you are always taking vectors from V. And it is a subspace because it is defined such. So you can see that it is defined such that it is a linear combination. I mean, there is this closed under addition thing because anything that is a linear combination of these vectors will be in the set. Hence, it is a subspace. Okay, now consider this. Now say I have V as my R2 and the vector is x comma y. These are like this. I take this vector, okay, 1 comma 0 and 2 comma 0. Okay, so now let's see what happens. Okay, let us see the linear combination of these two vectors. Now I've changed the vectors. Earlier it was 1 0 and 0 1. Now it is 1 0 and 2 comma 0. Okay, focus on this and let us see what will be the span. Okay, so my vectors are over here. So I have 1 comma 0 and 2 comma 0. So 2 comma 0. Okay, now you can see what happened. So when you do this, you are on this line, and no matter how much you change the multiplication factor, you will always be on the line. Okay, So basically this is nothing but a1 comma a2. Let me just remove that for now. Okay, so no matter what you do, you'll always be on this line. You'll never go outside the line. Okay, you can see this. So here these two vectors, a1, I mean this one x1, x2 and x1, which are actually this 2 comma 0 and 1 comma 0, they are spanning this line. Okay, they are restricted to this line, and we cannot go outside the line by changing the multipliers, right? So earlier this was not the case. Earlier we could span the whole R2, but now we are restricted to this x-axis. Why is that? Why did that happen? So the reason for that is because 2 comma 0 and 1 comma 0 are actually representing the same vector. So let me come back. So if you see, you can actually create this vector 2 comma 0 from this vector. I mean, there is no new information. One can take it like that. So 2 into 1 comma 0 is equal to 2 comma 0, where 2 is a scalar coming from the field. So this vector alone can represent this vector. So there is no need of this vector, right? So there is no new information. And that is what we call as linearly dependent. So these two are linearly dependent. And if you also talk in Desmos terms, you see both the vectors are over here. This is 1 comma 0 and 2 comma 0. So they are the same, they are actually the same vector, only it is scaled. So one of the vectors, this one, is scaled by this. That's the only thing. So you are not getting any new information. So that is what we call as linearly dependent vectors. So these two are linearly dependent. Okay. Now, so what is linear independent? So we need two different vectors. So in this case, if I again change this order, say going back to 0 comma 1, so you see when I just change this, I get a new vector in the horizontal direction. I mean, this may not be in the horizontal direction. Okay, you can okay, let me do that. Okay, so let this be 1 and let this also be 1. Okay, so now I have 1 comma 1 and 1 comma 0. Still I can span the entire space. Okay, so here you can see now what will happen is when I change this, I will go along this axis. You can see. So now if I say I want to come over here, okay, so if I want to come over here, first I can move like this. Okay, where was that point? Okay, let us consider 3 comma 3. Okay, I want to go to 3 comma 3. So how will I do that? So this can give me the horizontal motion. So I come over here, and then this gives me like this. I wanted to go to 3 comma 3. Right, so it's 3 comma 3. So these are the values 3 comma 0 by which I can reach 3 comma 3. And that's the case. I mean, I can span the entire space, entire R2 space by these two vectors. Now this is only possible because these two are linearly independent. These two are different things. So only when do you have two different vectors you can span the uh, entire space, right? Right, so coming back to linear independence. So a set of vectors, these set of vectors are called linearly independent if and only if this thing is satisfied. Okay, so just let me give you an idea of where this came up. So this thing should be 0 only if all AIs are zeros. Only if all the AIs are 0. Okay, let us see the previous example. So this was my previous example. So 2 into one of the vectors was equal to the other vector, right? My previous example. So you can see this can actually represent the other vector. So if I put this on the other side, so I just subtract this on both the sides. So I get this. So this is giving me 0. Now this is giving me 0 even if I have scalars that are non-zero, so 2 is not 0, here I have 1 which is not 0, and still I am getting 0, right? So that is the trick. Okay, this will never happen for linearly independent vectors. So say for this, so I have 1 comma 0 and I have 0 comma 1. Now you will never get any vector a1, any scalars a1 or a2 which will give you the answer as 0 comma 0. You'll never get that except when a1 and a2 are zeros. So a1 comma a2 is equal to 0 is the only solution to this thing, and that is what we call as linear independence. So if you want to check whether two vectors are linearly independent, what you'll have to do is you'll have to basically keep them like this, make an equation like this where the right hand side is equal to 0, and check if you get any solution of a1 and a2 other than 0, then they are linearly dependent. If there is no solution, if there is only one solution, that is 0 comma 0, that means that they are linearly independent. So that is a basic introduction to linear independence. So that's all for this video. I hope you got you got something to learn, and in the next video we'll see what is basis. So I'll catch you there. Thank you so much for watching. Thank you.